Hello and good afternoon friends, welcome once again to CEC-UGC live lecture. Dear friends, as you know that in our previous lectures we talked about nomenclature. I would like to tell you all that we are carrying a short series on this very topic. We discussed about nomenclatures in our previous session, and we are going to carry this lecture further. I mean the point from where we have left, we are going to start from that very point and would be talking more on the nomenclatures. For this we have with us in our studios Dr. Aprajita Chauhan. She is Associate Professor in Aurobindo College, Delhi University. So first of all, I would like to welcome Dr. Aprajita Chauhan, and I hope that the way she elaborated and gave us deep insight into the topic that is nomenclature, I hope that today also we are going to get deep insight into this very topic. Welcome ma'am, welcome once again to the EduSet lecture.
Welcome to the lecture today. We'll continue with where we not left last time, but we'll quickly revise what we did last time, because today we'll just take the naming of the main carbon chain, and from there we'll continue to monofunctional compounds and then to polyfunctional compounds. Now coming back to choosing the main carbon chain, please keep in mind, as we did last time, that the main carbon chain is to be that chain in which we have, in which the carbon chain has larger number of substituents attached to it, whether it is the straight chain or it is the branch chain. And the second point that you have to keep in mind is that if two substituents are getting the same number, then you will give priority to that group which comes first in the alphabetical order. For example, here we've taken an example where ethyl is also getting number 3, and if I number it from the other side, then methyl is getting number 3. But here I will give stress to ethyl and will give lower number to ethyl, and the numbering would be 3-ethyl, 4,5-dimethyl heptane would be the complete name of this compound. Now if I talk of the next compound, then what we see, we have a substituent on substituent, that is we have a alkylated substituent. Then in this case, please keep in mind that the carbon which is attached directly to the main carbon chain would be given number 1, dash. So now when I name this compound, and this substituent group will become methyl propyl, right? And the second point that we have to keep in mind is that while we are naming the complex substituent, then the first letter of the complete name is to be considered while giving the priority to in the alphabetical order. So what we see in this case is that the name we are giving priority to methyl and to D, and that means it becomes 2,7-dimethyl, 5. In dash we'll put 1-methyl, 1-methyl propyl. That is what you have to keep in mind. Please keep this in mind that 1-methyl propyl is your complex substituent, right? Okay. Now if I talk of the next slide, here we have 2 times the complex substituent is repeating 2 times. Now if I write di, it looks very weird. I'll write dimethyl, dilethyl. No, not that. So what we are doing is we are using another word bis, which in itself says that we are using this substituent is coming twice. Again, so how do we name this? We do the numbering from left side to the right side, and we name this compound as 2-methyl, and then in the we take 4,4. 4,4 we are repeating that this substituent which is repeating twice is attached to 4th carbon, and it becomes 4,4-bis 1-methyl ethyl heptane. So this now in the further slides again I have shown you a few examples which you can try yourself, and now we'll go on to naming of alkenes. When we name alkenes, please again keep this in mind that the double bond is to be included in the parent chain, and the lowest possible number is to be given to the double bond if no other functional group is present along with it. Right. So now what we've done here is we've given number 1 to double bond, and the name becomes 3,4,4-dimethyl pent 1-ene. Now if I look into the next example, please keep in mind that we are taking a branch chain, this chain, branch chain as the parent chain, and then we are starting the numbering from the side which is giving lower number to the double bond. right? So now the name becomes, at the 5th carbon you have a methyl group, so we name it as 5-methyl, and at the 3rd carbon again we have a complex substituent which we will name as 1-methyl propyl, and the name would become then 5-methyl, in bracket it goes 1-methyl propyl heptane, because the longest carbon chain has 7 carbons in it. Now, supposing the compound has 2 double bonds, we will try our level best to take those 2 double bonds in the main parent chain, right? So the name simply becomes, if I look into the first example, it is simply buta-1,3-diene. But if we look into the next example, which is the 5th example, this is very interesting. Now in this case, you see, we are not able to include all the double bonds in the main carbon chain. So what are we going to do here is, I am going to take 3 carbons in the main carbon chain, and the main carbon chain would have 8 carbons in it, right? So it becomes oct 1,3,6-triene. And since the substituent also has the double bond, as we did in case of alkane, we will remove a H from alkene, and since this substituent has 2 carbons in it, the name will become 5-ethenyl. Is it clear? 5-ethenyl, since we've removed 1 hydrogen from alkene, and the name is 1-octa-1,3,6-triene. Similarly, what we do is, we can name alkynes also in a similar manner, following the same rules. And now if we go on to a compound which is having a double bond as well as a triple bond, this makes a very, very interesting topic, and you have to take into consideration how do we do the numbering. In case both the substituents are getting the same number, if I number it from either side and they are getting same number, that is, if I number it from one side, if I look into the second example here, then the double bond is getting number 1, and if I number it from the other side, then the triple bond is getting number 1. But in this case, we are going to give priority to double bond, and the numbering will be done from left to right, and the name will become but-1-ene-3-ine. But there's another case when both the groups double bonds are not getting same number. Then in that case, we have to follow the lower sum rule. That is, we'll number from the side which gives the lower number at first point of difference. So if I look into example 1 again, what we have done here is, we have given numbering from right hand side to left hand side, in which triple bond is getting number 1. But while naming it, please remember, ene will come first. So the full name will become 4-methyl pent, since it has 5 carbon atoms in it, 3-ene-1-ine. This is the first example that we've taken into consideration. Now if I go on to next example, that is the 4th example. Now if you look into the 4th example, we have a case in which we can have a double bond as well as triple bond. Now we have a choice, we have to make a choice, because I have 1 triple bond in this and 2 double bonds in it. So which chain is going to be the parent chain? Please remember the rules, which says that the longest continuous carbon chain is to be taken as the parent chain, which has maximum number of functional groups in it. So if I take into consideration the straight chain, this is the parent chain. Again, we'll do the numbering giving priority to the double bond. So we start numbering from right to left, and at the 4th carbon we have a substituent which is the ethenyl group. So now we will name this as 4-ethenyl hept, since it has 7 carbons in the straight carbon chain, 1-ene-5-ine, which gives me the number of the double and the triple bond. This we have discussed in the last class also, and now we are discussing again. These were the naming of the main parent chain or the root name. Now what we have seen, that if we replace one hydrogen of either alkane, alkene or alkyne, then we get different derivatives of hydrocarbons. For example, if I replace a hydrogen with a halogen atom from an alkane, it becomes alkyl halide. Now the point to be noticed here is that, as we discussed in the last lecture, that we can have 3 types of carbons in an organic compound, that is primary, secondary and tertiary carbon. Now, if this halogen atom, or for that matter, a hydroxyl group is attached to a primary carbon, then the compound is primary. If it is attached to a tertiary carbon or a secondary carbon, then the compound is secondary. And if it is attached to a tertiary carbon, then it is a tertiary compound. Now, these compounds, alkyl halide is always taken as a substituent. It is never taken as a parent, so we name it as haloalkane. And while numbering also, we do not have to give it priority. We have to follow here again the lower sum rule. That is, we have to do the numbering from the side which will give lowest number to the substituents. That is, for example, what I am trying to stress here is, if we look into example number 3, right here, I have not done the numbering from the right hand side, which would have given number 3 to bromo group. We've done the numbering from the left hand side because this group here is getting the lowest possible number. It is getting number 2. So please remember, in case of alkyl halides, we do not have to give lower number to the halogen atom. So the name here would become, again in alphabetical order, we have to, while naming it along with the locant, it becomes 4-bromo 2,3-dimethyl hexane. And see, this is an example of a secondary alkyl halide, because in this case, if you look, this bromine is attached to a secondary carbon. If I look into the second example, which is 2-chloro-2-methylbutane, in this case, chlorine is attached to a tertiary carbon, and this is an example of tertiary alkyl halide. The next very interesting derivatives of alkanes are alcohols, which are obtained by replacing one hydrogen with an OH group. We can see these are of the same type. They can be primary or secondary or a tertiary alcohol. Right. Now, when we are talking of alcohols, alcohols are named as alkanols. If only OH group is present in the molecule along with a double bond or a triple bond, then we have to keep in mind that we will give greatest priority to the OH group, that is, we will give it the lowest possible number. And all other substituent groups like alkyl, and if halogen is present, that will be given lower numbers. So this compound, if I look into the second example, I'll choose the longest carbon chain, which I'm choosing from top to left hand side, and the OH group is on the second carbon, so it is 2, and since it has 4 carbons in the main carbon chain, the compound becomes butane 2-ol. Again, please keep in mind that since this is attached to a secondary carbon, so this can also, if I talk of a common name, this can be named as secondary butyl alcohol. And if we look into the third example, in this case, the OH is attached to a tertiary carbon, so this will become tertiary pentyl alcohol, or the IUPAC name would be, now if we have to choose again the longest carbon chain, it will be from top to bottom, and the name would become 2-methyl pentane 2-ol. Sorry, butane 2-ol, since the longest carbon chain has 4 carbons in it. Now, if we replace 2 hydrogens with 2 OH group, then it becomes a dihydric alcohol, right? And we name the compound as alkane diol. When we talk of diols, diols can either be vicinal diols, that is, the 2 OH are attached to the same to the adjacent carbon atoms, or it can be isolated, that is, 2 hydroxyl groups are attached to 2 carbons which are far away from each other. Please remember, we cannot have gem diols, because gem diols means that is the 2 OH are attached to the same carbon. That cannot happen, because then that compound is unstable and it loses a water molecule to form a corresponding aldehyde or a ketone. Now, when I am talking of alcohols, if I look into the second example is an example of a diol. It has 3 carbons in the longest carbon chain, so name becomes propane 1,2-diol. And if I talk of the fourth example, then this is an example of triol, which is propane 1,2,3-triol. Next compounds are ethers. In ethers, what we have is that oxygen is attached to 2 hydrocarbon groups. And you already know that ethers are functional isomers of alcohols. When I talk of ethers, the 2 alkyl groups can be same on the either side of the oxygen, that is example number 1 and 2. then in that case, then in that case we say that it is an example of symmetrical ether. But in case the two alkyl groups on either side of oxygen are different, then that is a case of unsymmetrical ether. For example, in second case what we find is on one side we have a methyl group and on the other side we have an ethenyl or a vinyl group. Right? So this is an example of an unsymmetrical ether. Now the question comes, how will we name ethers? Please remember, it is always the smaller alkyl group along with oxygen, which is taken as alkoxy, and it is added before the root name, so the name becomes alkoxy-alkane. For example, if I talk of this unsymmetrical ether only, this will become methoxy-ethene because methyl group is smaller than the double bond, which is having two carbons in it. And secondly, even if it was an ethyl group, I would have taken this as ethoxy-ethene because ethene is we give priority greater than methyl group. Now, if I go on to next, naming of some alkoxy groups, first is ethoxy. Second is, now if I have to take this, my ethoxy group is branched. Then in that case, we will do the numbering in the similar way in which we did in case of alkyl chains. That is the O, we have to first donate the oxygen, number of the oxygen to which carbon it is attached, and then again the name of the substituent. Now if I look into this example, I have two chains on the either side of oxygen which are branch chains. In one chain I have 3 carbons and in the other chain we have 4 carbons. So first of all, we will choose what is the alkoxy group. We will take that group as the alkoxy group which is having less number of carbon atoms. So in this case, it will become 1 methyl, and in the main carbon chain it has 2 carbons, so 1 methyl ethoxy. This is the alkoxy group. Now this oxygen is attached to second carbon of the main carbon chain. So first we have to indicate where is this oxygen attached. So it is attached at position number 2. So 2 comes first, and then in the bracket what we are doing is we are taking 1 methyl ethoxy, which is the alkoxy group, and then the butane. Second case, again if I look into it, again what we've taken here is, here the substituent is simple, we've just taken it as ethoxy. We've numbered the longest carbon chain from top to bottom, it is attached at the second carbon, so the name becomes 2-ethoxy-butane. But the point that is to be taken into consideration is this example, because see, here we have to differentiate between 2 methyl groups. One methyl is the one which is attached to oxygen, and this is the alkoxy group. This is the main functional group, right? So this will come first, and we will name it as 1-methoxy since it is attached to the first carbon of the main carbon chain. Now the question arises, how do I name this chain, the parent chain? The parent chain, in parent chain we are taking 3 carbons, and then we will add, after we've done the added methoxy, we will say it is 2,2-dimethylpropane. So the full name becomes 1-methoxy-2,2-dimethylpropane. So what you have to keep in mind is, when we are having 2 alkyl groups, the alkyl group which is attached to oxygen will be given priority over the alkyl which is attached to the main carbon chain. The next functional group that we are going to discuss is the carbonyl groups. Now in carbonyl group, the functional group is CO. This is again another set of functional isomers that we are going to discuss here, aldehydes and ketones. In aldehydes, the functional group is CHO, and in ketones, the functional group is CO. That is, in CO, the 2 alkyl groups can be different or they can be same in case of ketones that we'll be discussing later on. Now, if I talk of an aldehyde, we have to keep in mind that aldehyde group has to be taken in the main parent chain, and it will always be given number 1 if this is the group present in the molecule along with the groups which have been discussed previously. So what we see is, in case of first aldehyde, that is example number 1, this is having 3 carbon atoms and we number it from right to left and it is named as propanol. If I go on to second aldehyde, that is an unsaturated aldehyde, and here we are again giving priority to the aldehyde group and the name becomes but2-ene-1-al. Now Second example is an example of, third example is an example of dialdehyde, and fourth is an example of aromatic aldehyde, benzaldehyde, which we will be discussing later in detail. Now, if I come to this example you see we have taken the branch chain as the parent chain, giving number 1 to the aldehyde group. So, the compound becomes 2-methyl-butanol. If I take example number 2 in this case, then please remember, then in example number 2, what we've done here is, we've taken the branch chain as the parent chain, we are starting numbering from aldehyde group, and we are getting substituents at the second carbon and the fourth carbon. So, the main parent chain is pentanol, because it is having 5 carbons, and the name of the compound would be 2-ethyl 4-methyl-pentanol. Now, if you look into the third example is again, we have 2 chains will be having same number of carbon atoms. That is, they can form 2 we have a choice between 2 parent chains. Then in this case, we've taken that parent chain which is having larger number of substituents attached to it. That is, we've taken from right to left the branch chain. So, when we number this, and we've again given number 1 to the aldehyde group, so the compound becomes 3-methyl 2-propyl-pentanol. Right. So, please keep in mind that if there are 2 chains which are having same number of carbon atoms, then you will choose that chain which has the main functional group along with the maximum number of substituents attached to it. Now, if we talk of ketones like ethers can be symmetrical. That is, if we look into example number 1, the 2 alkyl groups on the either side of the carbonyl group are same. Right. So, this is an example of symmetrical ether. If I talk of the next example, then the 2 alkyl groups are different. This is an ethyl group and the next one is a methyl group. So, this is an example of an unsymmetrical ether. So, while if we do the numbering from this side, we will do the numbering from right hand side to left hand side, so that the carbonyl groups, that is the ketonic group, gets the lowest possible number. Next is an example of unsaturated ketone, then a cyclic ketone, and then we talk of aromatic ketones, which again we will be discussing later on. Now, if you look into this example, which is your example at the bottom, now the question comes, from where should we do the numbering? See, if we do the numbering from right hand side to left hand side, then the methyl group is getting number 3. And if I do the numbering from left hand side to right hand side, then the ketonic group is getting number 3. What we have to keep in mind that the ketonic group should get the lowest possible number. So, we do the numbering from the left hand side and the name becomes 5-methyl heptane 3-on. Now, if I talk of this next example, which again we've taken as a branched example, because what I have to stress that what concepts that you have to make clear in your mind is, while that is of the choice of the main carbon chain. So, in this case again we've taken a branched carbon chain, right. In this branched carbon chain there are 8 carbon atoms in it, and we've taken this chain as the parent chain because this has maximum number of alkyl substituents attached to it. So, now the name will become 6-ethyl, please remember in alphabetical order, 3,7-dimethyl octane 4-on. Please remember again, we are not writing dimethyl before ethyl because you have to compare the alphabets of the main substituents, and the main substituents here are E and M. So, E comes first. Di is merely telling us how many times this substituent is being repeated. Now, talking of next functional group of hydrocarbons, then there are carboxylic acids. Carboxylic acids are formed if we replace one hydrogen of the alkane with the carboxylic group COOH. And the general formula of these compounds is CnH2nO2. And they are named, we drop the word E from alkane and they are named as alkanoic acids. We drop the word from E from alkenes if they have a double bond, and we name it as alkenoic acid. Again, here our main aim is going to be that we are going to give the lowest possible number to the carboxylic group here, like in this example. So, what we've done is we've taken chain from right hand side and we are going towards the top. and the substituent is present at the second carbon and the fourth carbon, and the substituent is methyl. So the name becomes 2,4-dimethyl, and since the longest carbon chain has 6 carbons, it is known as hexanoic acid. Please remember here, we are including this carbon, which is carbon of the functional group, in the main parent chain. So in the main parent chain, we have 6 carbons. Similarly, in the next example here, again we will do the numbering from top to right hand side, because carboxylic group is at the top and we have to give the lowest possible number to the carboxylic group. So the name becomes 2,4-dimethyl-butanoic acid. Similarly, in the next example also, when we talk, we write down 2-ethyl-3-methyl-butanoic acid. Now, if by chance 2 hydrogens are replaced with 2 carboxylic groups, then it becomes a dioic acid, and we name the compound simply as dioic acid. Now, if in this slide, if you see, we've shown examples of dioic acid. The simplest dioic acid that we can have is ethane 1,2-dioic acid or oxalic acid, right? Next is propane 1,3-dioic acid, then butane 1,4-dioic acid, and in all these cases we are including the carbon of the carboxylic group in the main carbon chain. Now the question arises, if we had 3 carboxylic groups in the molecule, what are we going to do now? Are we going to include this in the main carbon chain? Then no, the answer is not. What we are going to do is, we are going to take the main parent chain, which is having maximum number of carbon atoms, that is the alkane part. So in this example, what we've done is, we've taken 4 carbons and we've taken it as butane. And the 3 carboxylic acids are, please remember, these 3 carboxylic acids are not included in the parent chain. This is to be kept in mind. This is a very important point. And they will be named separately. That is, we will name it as, we are not including it in the parent chain. So this is named as carboxylic acid. This is not included in the chain. And since it is being repeated 3 times, we write it as tricarboxylic acid. So the name becomes, since the parent chain has 4 carbons in it, it is butane, and 3 carboxylic acids is 1,2,4-tricarboxylic acid. Now the next point is, that is to be kept in mind is, supposing we have again 3 carboxylic group. This is the group, the example which is just below this, and the 3rd carboxylic group is not forming the part of the parent chain, right? So in this case, the 2 carboxylic groups which are forming the part which can be included in the longest continuous carbon chain will be included in the parent chain. So the root name will become hexane 1,6-dioic acid. And this substituent, which is at the 4th carbon, this will be named as carboxymethyl. This is taken as a substituent group. So what are we going to write this name as? We are going to write it as 3-carboxymethyl. This is a substituent group here, and hexane 1,5-dioic acid. Right. Now we go on to the functional groups, the functional derivatives of carboxylic groups. Carboxylic group in itself is very interesting. Most of the carboxylic acids are found in nature, and its derivatives are also found in nature, which have very important biological role. Now, if I talk of the groups that can be derived from acids, we can derive them by replacing, by nucleophilic substitution of the hydroxyl group of the carboxylic group by different functional groups. These functional groups can be a halogen, right? Then in this case, it is named as alkanoyl halide. Second, what we can do is, we can heat 2 acid molecules together. They lose a water molecule and they become anhydride. Like if I remove a water molecule from copper sulfate, it becomes anhydrous copper sulfate. Similarly, if we remove a water molecule from an acid, it becomes an anhydride. Next, what we can do is, we can replace a OH of the acid if we treat the acid with alcohol, and we get a group called OR or OAR, and this is an ester. And then next is, if we treat acid with ammonia, we get the functional group which is amide, CONH2. Please remember all these compounds are known as acyl compounds since they have the group acyl in them. So the first is acyl halide, second is acid halide or acyl anhydride, third is an ester, fourth is an amide, and all of them have an acyl group in them. Now if we talk of acid halides in detail, then please remember acid halides are named as alkanoyl halide. That is, we drop the word E from alkane and replace it with oil halide. This halide we have to specify. It can be chloride, it can be bromide, it can be any halogen atom. Now if I talk of this compound, that is the first compound that we are talking of, then what we see is that this is, we will start the numbering. Again, please remember, numbering has to be started from that carbon which is your functional group. So we start the numbering from COCl and we go from here straight and then on the top, and the name will become, again we have to take a substituent group. This substituent is ethyl, which is at the second carbon. At the fourth carbon we have methyl group, so it becomes 2-ethyl 4-methyl hexanoyl chloride. Similarly, in the next carbon, again next chain, again I could have taken the straight chain as the parent chain. But here again we've taken a branch chain as the parent chain, because in branch chain we have two substituents. One is methyl and the other is ethyl. So now while we are naming this compound, please remember the root name of this compound will become butanoyl chloride, and the substituents are at the second carbon, which is ethyl, and the third carbon, which is methyl. So the name will become 2-ethyl 3-methyl butanoyl chloride. Is it okay? Now the next is, instead of taking chloride, we've taken bromide. So the name becomes butanoyl bromide along with the substituent groups. Now when we talk of anhydrides, as discussed earlier, anhydrides are formed from acids. If anhydrides are formed from two molecules of the same acid, then it is known as symmetrical anhydride. That is first example. For example, if I take O as an heteroatom, then the groups CH3CO, CH3CO on the either side of oxygen is same, and we call it as symmetrical anhydride, and it is named simply as alkanoic anhydride. So in this case we are naming it as ethanoic anhydride. That means that it is derived from ethanoic acid by losing a water molecule. Now if I look into the third example is an example of mixed anhydride. Mixed anhydride means that we have heated acids of two different types, two different acids, and on the one side we have ethanoyl group and on the other side we have propanoic group. Now here it will be named as alkanoic anhydride, right? And again we will take the alphabetical order, so it will become ethanoic propanoic anhydride, right? So next very interesting class of compounds is esters. We wear perfumes every day. We have some flavoring agents in ice cream, vanilla flavor and all. Do you know what they are? They are esters and they occur in nature. So now these esters again are derived from acids by replacing OH with an alkoxy group or with a phenyl group. Now how do we name these esters? Please remember the alkyl group which is attached to oxygen, that is to be taken as alkyl, and the name is alkyl alkanoate. And the group, the hydrocarbon part which is attached to the carbonyl group, that will be taken as the parent chain, that is the parent acid. So in this case, the first case, the ethyl group is attached to the oxygen, so the name becomes ethyl ethanoate. Now if you look into the second example, this is a complicated example. In this what we've done is, we've even taken the chain, that is the alkyl chain which is attached to oxygen, as the branch chain. So in this case it will become, now see again here 2 points that have to be taken into consideration is, one is the group which is attached to oxygen, the alkyl portion, that is an ester. So that will come first, and the alkyl part which is attached to the main carbon chain here, which is the methyl, this will come later on and it will be written along with the name of the alkanoate. So now here the name is 2-methyl, it is 1-methyl because it is attached to the first carbon of the ethyl group. It is 1-methyl ethyl Is it okay? And then at the second carbon, we have this methyl group. So we write it as 2-methyl propanoate because the main carbon chain has 3 carbons in it. So the name becomes 1-ethyl-methyl 2-methyl propanoate. This can also be, if I talk of the common name, this can be written as isopropyl isobutyrate. Next example again we've taken, and in this case again the alkyl part is your substituted alkyl group, and in this case again it becomes 1-methyl propyl and then methanoate. Next example is an example of a cyclic ester. These again will be discussed in detail later on, but in this case, since we are not taking carbon as the part of the parent chain, this will be named separately as carboxylate group. So this again we will be discussing in detail, but I'll just briefly tell you what is the name of the compound. This is 2-methyl propyl cyclohexane carboxylate. Here carboxylate has been named separately because its carbon has not been included in the either of the carbon chains. Now next example is amides. What are amides? Amides are derivatives of acids which are formed by replacing OH with an NH2 group. Now these amides can be simple amides or they can be substituted amide. That is, simple amide is methanamide, ethanamide. Now if I talk of the third example, this is an example of a substituted amide. What we've done, how did we get this amide is, we got this amide when we treated acid with a primary amine and the group was replaced with, the hydrogen of the primary amine was replaced with C2H5 group. Now what we have to please keep in mind here, what we have to distinguish is between the alkyl group which is attached to nitrogen and the alkyl group which is attached to the carbon atom, right? So here while doing this demarcation, what we have to keep in mind is the alkyl group which is attached to nitrogen will be specified by writing N before it. So the name will become N-ethyl propanamide. Propanamide, that is, the main carbon chain has 3 carbons in it and the functional group is amide. Now the point that I was stressing in my previous example, I like to take it up here again in this example is, that is, if I have this example, then see here we have to distinguish between the two groups, ethyl which is attached to nitrogen and a methyl group which is attached to the main carbon chain. So if I talk here, then what we have to keep in mind here is that the ethyl group which is attached to nitrogen will always come first because this is my main functional group. So what we'll write here is N-ethyl 2-methyl propanamide. Again, we've taken an example of a di-substituted amide in the next example in which you have 2 alkyl groups attached to nitrogen. So see here again we have to make demarcation within the 2 alkyl groups. One is attached to nitrogen, one is attached to carbon. So one which is attached to nitrogen, we will write this group as N-ethyl, N-methyl, again here we are taking alphabetical order, and then 2-methyl propanamide. Is it okay? So this is clear. Now we go on to next functional group, that is nitriles. Nitriles do not have a carbonyl group in it, but still they are considered to be the derivatives of carboxylic acids because they on hydrolysis give complete hydrolysis give us carboxylic acids. And please remember, as in carboxylic acids, since the carbon is forming the part of the main carbon chain, this carbon is to be included in the main carbon chain. So now the name becomes, first molecule has 2 carbons in it, so we name it as cyanides, that is nitrile. So if I name this as nitrile, this is having 2 carbons in it, so it is ethane nitrile. Next is an example of propane nitrile, next butane nitrile. Now if I talk of the 5th example, then in this case we have a alkyl group and we will name this alkyl group as 3-methyl butane nitrile. Now another set of compounds which are isomeric with cyanides, they are isocyanides. Now in isocyanides, please look here that this carbon atom is attached to nitrogen. So there is heteroatom between the two carbon atoms. So this carbon atom of the functional group will not be included in the parent chain. So now the name becomes methane isonitrile. Although it is having two carbons, since the main carbon chain alkyl part has only one carbon, so it is methane isonitrile, and the next one is ethane isonitrile. Now another important class of compounds are amines. Amines are very important because they form part of various biologically important compounds, like if I talk of proteins and different drugs, they have a functional group which is amines, which is very, very important. What are amines? Amines are derivatives of ammonia by which we replace one hydrogen or two hydrogens or three hydrogens of ammonia with different functional groups like alkyl, cycloalkyl or a allyl group. Now the question is that we have three types of amines then: primary amine, secondary amine or a tertiary amine. Interestingly, these primary, secondary and tertiary amines are functional isomers. Remember, initially we had discussed primary, secondary and tertiary alcohols. They are not functional isomers because in them the functional group is same, that is OH. But if you look into these examples, then if I look into the first example, this is an example of primary amine where the functional group is NH2. If I look into my example number 6, I think, then in that case you have cyclohexyl group in it and the functional group is NH. That is a secondary amine. So here the functional group has changed. So primary, secondary and tertiary amines are functional amines. So the naming is quite simple: ethanamine, propanamine, butanamine and so on. But see, I want to now clarify here the example in which I have put a cross. This is an example of a secondary amine. If you see what we've written, N2-dimethyl propane-2-amine, this is absolutely wrong. Because here again, please remember, you have to make a distinction between the alkyl group which is attached to nitrogen, so that will be written as N-methyl, and then you have a methyl group which is attached to the carbon. So it is not dimethyl, it is methyl, it is N-methyl, N-methyl, propane-2-amine. So please keep this in mind. This is where you may lose marks if you make this mistake. Next is an example of a cyclohexylamine and then a example of aromatic amine, that is aniline, which will be again discussed in detail later on. Now if I go on to polyfunctional compounds. Till now what we've discussed is, we have discussed monofunctional compounds. Monofunctional compounds are those compounds which have one functional group along with the root name. That is, root name may have a double bond, a triple bond. So double bond and triple bond is the primary suffix, and when I add any other functional group, that is the secondary suffix. And all other groups which come before the root name are the prefixes. But now the question comes, how would you choose a prefix and a suffix? You cannot randomly choose, okay, let me take this as a prefix or let me take this as a suffix. Your whole question or your whole answer would be just wrong and you will not get a single mark in it. That we have to now stick to the IUPAC nomenclature and follow their rules. What they say is, they have given us a priority table for polyfunctional compounds. That is, if a compound is polyfunctional, it may have 2 or 3 functional groups in it. Now, 2 or 3 same functional groups or 2 or 3 different functional groups. If the functional groups are different, how are we going to choose the family name? Please remember, the family name is always 1. We can have number of substituents. So family name has to be 1. It will always come in the suffix. Prefixes, rest all the groups after we've chosen the suffix will be prefixes. They will come in alphabetical order along with the locant in front of the root name. Right. Now here what we've done is, we've taken the priority table. Now if you see this priority table, you will have to memorize this. You cannot carry it with you in the examination hall. And the order should be absolutely correct. What I mean by saying order should be correct, COH group comes first, after that the group is SO3H, then the group is ester, then the acid halide. You cannot make it amide coming first before acid halide, because then the whole naming would be wrong. Then instead of taking acid halide as a parent, what I'll do the mistake of taking amide as a parent. That you cannot do. So now when we choose this, please remember the group which is coming first in the priority table. Supposing I have a compound which is having a COH group as well as CN group in it. So what will I do? I will take the suffix of the group COH, which is oic acid, and the prefix from the compound CN, which is cyno. So cyno will come before the root name and suffix will become after the root name. So name will become cynoalkanoic acid or alkenoic acid, whatever the case may be. So please remember, you have to memorize these groups, and till what we see till amines, we have to choose between the groups, that is the suffix and the prefix. That is the group whichever is coming first, we will take its suffix, and the rest of the groups will be taken as prefixes. Now the groups after this, please remember, always double bond and triple bond have to be included in the root name. So we have only suffixes for that, no prefix for that. And rest of the groups which are coming below this, like azo, nitro, methyl, they will be always taken as prefixes. That is, they are always substituent groups. They will never be taken as parent groups. Now let us take some examples of polyfunctional compounds. Now if I talk of a polyfunctional compound, what I see here is, I've taken a polyfunctional compound in which I've taken two functional groups in it. One functional group is COOH and the other functional group is OH. Now if I go back to my priority table, then what does my priority table shows? It shows that the COOH group is coming first in the priority table. So what will I take? This will become my principal group, and I will choose what is written in the suffix column, and that is oic acid. And what is in the suffix column, a prefix column of the OH group, that is hydroxy. So now the name would become, since this compound has 5 carbons in it, it will become 4-hydroxy pentanoic acid. So pentane is indicating that there are 5 carbons in the main carbon chain. Carboxy is my parent group, so I've written it after it, and OH is the subsequent group. Similarly, here also, in the same example, next example also we've shown you that we are taking the substituents and the parent group. Now we have, next is, now we will discuss it with examples only, more and more examples of the polysubstituted compounds. Now in this case, what we see is there are 2 functional groups and both of them have C carbon in them, and these carbons can be included in the main parent chain. But now again we have to make a choice between the parent chain and the subsequent chain. Here the parent chain is the carboxylic group. So the name will become, and the carbon chain has 3 carbons in it. Here I am including the carbon of this carbon substituent also in the parent chain. So the name will become 3-formyl propanoic acid, 3 carbons, and the parent group is carboxylic acid. So the name becomes propanoic acid. Now let us go on to next few examples. In these examples, we have 3 same groups repeating again and again, and which are having carbon in them. Now please remember, these 3 functional groups cannot be included in the main parent chain. They have to be named separately. So what do we see here? In the main parent chain, we have 4 carbons. So we take main parent chain as 4 carbons, butane, and 3 groups. These are the parent groups. They cannot be included in the parent chain, but I have to indicate that they have a carbon in it. So we will not name it as nitrile, but we will name this as carbonitrile, which is indicating that there are, in total we have how many carbons? 7 carbons. So the name becomes butane 1,2,4 tricarbonitrile. Similarly, in the next example, if you see, which is an example of carboxylic acids, here also again we've taken in the main carbon chain, we've taken 5 carbons, which is pentane, and then the 3 carboxylic groups are named separately as 1,3,5 tricarboxylic acid. Now the case of aldehyde, again here we cannot take it as the parent chain, so they are named separately as tricarbaldehyde, that is propane 1,2,3 carbaldehyde. If we go on to next example now, in this case what we've done is, now see again here I have taken what you have to distinguish. Initially there were 3 carboxylic groups or 3 cyano groups or 3 aldehyde groups which were attached to the main carbon chain. So when they were attached to the main carbon chain, they could not be included in the main carbon chain and we had to name them separately. But in this case again I have 3 cyano groups here, and when we have 3 cyano groups, one of the cyano group is not attached directly to the parent chain. In that case what we've done is we've taken this as a substituent group and we are naming this as cyanomethyl group. Is it clear? So what we've done is we've included the 2 cyano groups in the main parent chain. So the main parent chain will have 6 carbon atoms and it has hexane 1,6-dinitrile, and this group is taken as the substituent group which is added as a prefix like 3 cyanomethyl group. Similarly in the next example, if you see, in next example also we've taken an example of an aldehyde which is having 4 aldehyde groups, 2 of which are attached to the main parent chain. We've included it in the main parent chain and I've taken the straight chain as the parent chain. So that becomes hexane 1,6-diol. Then again if I talk of the substituent group which is put in a blue colored circle, what you see is again I have named this as formyl methyl group, right? So the name will become, and since this group is coming twice, please remember we had discussed this earlier also, that if a group comes twice and it is a complex group, we add the word bis. So the name would become 3,3-bis-formyl hexane 1,6-diol. Diol indicates that this has 2 carbon atoms in it. Now we go on to next. This is a replacement system. This is little different from the system that we've discussed till now. In this replacement system, what we do is, like for heteroatoms like a nitrogen or an oxygen, we don't name it separately. What we do is we include it as the part of the parent chain, and then we write, what we do is we take the total number of atoms which are in the parent chain that is included, and the atom at the locant at which the heteroatom is present, we give that number, and for nitrogen, for example, I will take as aza. So at 3rd carbon I have a aza group. So, I'll write it as aza, and then at 5th carbon I have a ethyl group. So what do we write now, this compound? We write this compound as 5-ethyl 3-azaheptane. So what have I done? In heptane, I've included the heteroatom also in the parent chain. And I'm indicating that heteroatom is present at the 3rd position by writing the name of the locant 3, and we've used the word aza here. Similarly, if I look for ethers, ethers we use the word oxa, right? And what we have here in the main chain, we have 9 atoms total in all, and we have a heteroatom which is oxygen at the 2nd carbon, then at the 5th carbon, and then at the 8th carbon. So what we've done here is 2, 5, 8 tri, and this is a heteroatom, we are using the word oxa for it, and then since the number of atoms in the main carbon chain are 9, it is named as nonane. Now again, here what we've done, we've taken few more examples of polyfunctional compounds. In this, what we've done is we've taken more than one functional group. So you have to now decide which is the functional group you are going to take. Are you going to take amino as the main functional group or the OH as the main functional group? All the groups which are put in the black circle, they are the principal functional groups, and the groups which are put in the blue circles, they are the substituents that will be considered as what we'll take up from the prefixes. And alkyl and groups will be named as we've been doing previously. So now the name becomes, if I have to choose the longest carbon chain, I've taken a highly branched chain going from left to right, and we name this compound as, we have a substituent which is amino, so we are naming it as 5-amino. Please remember the alphabetical order: 5-amino, 3-ethyl hexane, and then the OH group is at second carbon, so we are naming it as hexane 2-ol. Please see, look here again, please keep in mind that we have given the lowest priority to the group OH and not to amino. If I had numbered it from the other side, amino would have got number 2. But if we had done that, then the whole question would have been wrong, just by adding a wrong locant to the number. The incorrect locant would make my answer incorrect. Now if I go into the next example, here I have two functional groups. One is keto, which we've considered as the substituent group, and the other is the aldehyde group, which we've taken as the parent. So please remember again, the numbering will start from the parent group, which is this group. And now from here, we are going from here to the left hand side and on the left hand side. So we've taken this as the parent chain. We could have taken the lower chain also as the parent chain, but we've not taken that as the parent chain because the number of substituents there are less. So now if I look into the substituents, I have two substituents. First is at the second carbon, second is at the fourth carbon. So this becomes 2,4-diethyl, then 3-nitro, and then we have this oxo group, which is the ketonic group at the fifth carbon, 5-oxohexanol. So this is what the whole complete name is. Let us look into the next example. Now the next example shows me a compound which is having two ketonic groups in it. Now we will include both of these ketonic groups in the parent, and we will number it from left to right. So total number of carbon atoms here are 6. So hexane, and here we are taking dione. Please, if you we go into the previous example, I think I've skipped quite a bit. Here, see, I was taking this as an oxo group. So we will continue this in the next lecture.
Definitely, ma'am. We are going to continue this very topic into the next lecture, and as you have elaborated in detail, I hope that all the students who might have watched this lecture would be benefited from this particular lecture. And I would like to tell you all that you can access this particular lecture with the help of the YouTube. On YouTube, we daily upload our lectures. Thank you, ma'am. Thank you so very much.
Thank you so much.